Type a URL into a browser, and the internet has milliseconds to turn that human-readable name into an IP address. We are constantly told that this domain name system lives or dies at the very top. The assumption is that every lookup has to walk the whole internet, starting with a plea to those global root servers. But look at this resolver map. It tracks the actual path of a standard query. When a request comes in, it almost never goes to the global root. The root isn't the bottleneck. Recursive resolvers cache aggressively, and RFC 8806 even standardizes running root data locally, so live global root contact is not required for every query. This is no tech. If the root isn't the bottleneck, where does DNS actually get fragile when recursive resolvers, authoritative servers, caching, privacy, and locality all collide? If the root can be local and cached, what exactly has to stay live for DNS to keep working? Hold that thought. The answer is where the system stops being abstract and starts failing in real operations. Open a recursive resolver's terminal inside an enterprise network. If you watch the traffic, you will see a recurring pattern: the cache hit. This cache hit represents locality and speed, making the internet feel instantaneous. Every DNS record carries a time to live, a strict countdown timer dictating exactly how long a resolver can hold that answer in memory before discarding it. For a stable domain, that timer might be set to 86,400 seconds, a full 24 hours. For an entire day, that recursive resolver will never ask the outside world about that domain again. While that timer ticks, it answers directly from memory. We're told DNS lives or dies at the root, but recursive resolvers mostly live on cache. The classical mental model insists that when a cache finally expires, the resolver must reach out across the internet to the global root servers to find out where to go next. But look at this root cache record. A standards-compliant resolver can run root data locally. In 2020, the Internet Engineering Task Force published RFC 8806, updating explicit details on how to run a root server local to a resolver. Operators already did this informally to save the 30-millisecond round trip to a global root cluster. The IETF formalized and standardized the practice. By keeping a loopback copy of the root zone, the resolver never has to ask the global internet where the top-level domains live. Instead of traversing fiber optic cables across an ocean, the query routes internally, never leaving the physical machine. This completely undercuts the myth that every lookup must traverse the live global root system. Most DNS work avoids the global root path entirely. But eventually, a user asks for a domain not in the cache, or a timer hits 0. The resolver hits an empty branch. This empty branch symbolizes the exact point where recursion has to leave memory and ask an authoritative server for fresh truth. And that is where the operational reality changes. Move from the local resolver to the data center floor of a major cloud provider. Look at this Anycast status board on the wall. When an empty branch forces a recursive resolver to ask for directions, it doesn't just hit a single commodity web server. It hits an authoritative DNS infrastructure designed to absorb millions of queries per second. We often treat authoritative DNS as a simple, solved problem, just a database returning IP addresses. But the IETF had to write dedicated guidance just to explain how to keep it from collapsing. RFC 9199 exists because large authoritative operators face specialized scaling and resilience concerns that ordinary web hosting never encounters. As with the broken protocol routing the internet, DNS only works at global scale because operators have layered mitigations around a legacy protocol that never assumed hostile conditions. When a major domain lowers its time to live to shift traffic quickly during an incident, it forces recursive resolvers worldwide to expire caches faster. A 60-second TTL means the cache hit ratio plummets. Instead of answering from memory for 24 hours, the resolver must ask the authoritative server again every minute. Suddenly, millions of empty branches happen at once. It is a thundering herd of traffic that looks exactly like a distributed denial-of-service attack. The Anycast status board lights up as the authoritative servers absorb the impact. BGP route announcements actively shift this traffic to different physical data centers based on network topology, preventing any single cluster from melting down under the query volume. If a node is overwhelmed, Anycast routing simply withdraws the route. The BGP announcement is pulled, the router stops advertising the path, and the internet automatically redirects queries to the next closest facility, perhaps shifting traffic from Frankfurt to London within seconds. This makes large authoritative DNS scale and failure behavior visible as an operations problem, not a simple lookup problem. The system survives because of massive over-provisioning, careful traffic engineering, and strict limits on how fast a zone can update. But even if the authoritative servers stay online and the Anycast routing holds, there is another assumption baked into this exchange that is actively breaking down. Pull up the latest drafts from the Internet Engineering Task Force. When a recursive resolver finally leaves its cache and talks to an authoritative server, we assume that conversation is secure. After all, the industry has spent 2 decades deploying DNSSEC. But DNSSEC provides integrity, not privacy. It proves the answer wasn't forged by cryptographically signing the record, but it does absolutely nothing to hide what you are asking for. The link between the recursive resolver and the authoritative server remains traditionally wide open. Anyone monitoring the transit network can see the exact domain being requested. This is where the encrypted link becomes a critical operational boundary. The IETF treats recursive to authoritative privacy as a separate engineering problem. Through workstreams like DP-Rive, engineers are trying to standardize how these two massive pieces of infrastructure can negotiate encryption without breaking the speed of the internet. They are testing opportunistic and unauthenticated encryption. Why unauthenticated? Because even if a resolver cannot cryptographically verify the authoritative server's identity, simply encrypting the connection protects the query from passive surveillance. A recursive resolver attempts to open a TLS session on port 853. If the authoritative server supports it, the query is shielded. If it doesn't, the resolver must decide whether to fall back to plain text or drop the query. This negotiation adds latency to a system originally built around single, lightweight UDP packets. A classic UDP DNS query is fire and forget. 1 packet out, 1 packet back, 10 milliseconds total. A TLS handshake requires establishing a TCP connection, negotiating cipher suites, and verifying certificates before a single query is asked. That turns a 10-millisecond exchange into a 40-millisecond negotiation. Multiply that by millions of queries per second, and the CPU overhead on the authoritative server becomes a massive constraint. This is why privacy in this part of DNS is an active engineering concern rather than a solved property of classic DNS. The IETF has documented explicit privacy requirements for exchanges between recursive resolvers and authoritative servers, balancing confidentiality against the brutal math of latency. And this privacy boundary gets even more complicated when we look at modern enterprise architectures. Sometimes, the authoritative answer depends entirely on who is asking. Historically, split horizon DNS was treated as a fragile hack, a setup where internal users saw one zone file and external users saw another, often breaking validation. But RFC 9704 formalizes validated split horizon and local authority behavior. It shows that controlled local answers are now an explicit architecture. Local DNS can still be valid DNS, with formal trust boundaries separating internal infrastructure from the public internet. With RFC 8806 local root data, RFC 9199 operational guidance, and privacy work for recursive to authoritative exchanges, the real pressure point is not just the root. The pressure point is the boundary itself. Step into an incident response channel during a major regional outage. Bring back that resolver map we opened with. We assume outages happen because the internet's core infrastructure fails, but tracing the evidence on that map changes the story of DNS failure. Caching and the root cache record remove the root from the center of every lookup.
RFC 9199 and the Anycast status board show authoritative DNS at scale is an operational discipline, requiring massive fleets just to survive cache expirations. And dprev and the encrypted link show privacy between recursive and authoritative is still an active design problem. Which brings us back to the question we delayed at the start. If the root can be local and cached, what exactly has to stay live for DNS to keep working? The fragile layer is the recursive to authoritative boundary, where freshness, reachability, encryption, and local control decide whether DNS stays fast or fails loudly. When a recursive resolver hits an empty branch, it must cross that boundary, leaving the safe, fast local cache to venture out into the complex, routed internet. If the authoritative server is overwhelmed by a thundering herd of expired TTLs, the resolution dies. If the encrypted link fails to negotiate properly and drops the connection instead of falling back, the resolution dies. If a split horizon policy misroutes an internal query to a public server, the resolution dies. The internal database address leaks to the public internet, returning an NX domain phodomain error because the public authoritative server doesn't know what that internal hostname means. And when it dies, the impact is immediate. A microservice fails to locate its database. A load balancer drops incoming connections. A user stares at a spinning browser wheel. The system does not fail because a global root server went offline. It fails because the operational handshake between the recursive cache and the authoritative truth breaks down under the constraints of modern infrastructure. DNS breaks at the boundary, not the root. Look again at those cached answers. The root is not the bottleneck. Recursive resolvers can cache heavily and even keep root data locally, while the real engineering risk sits in the recursive to authoritative chain, where scale, locality, privacy, and operational budgets collide. If resolvers can keep root data locally and still depend on authoritative DNS exchanges for freshness, what breaks first when latency, reachability, and privacy start competing at the recursive to authoritative boundary? We follow the evidence in standards, operational guidance, and wire-level design to show how compute infrastructure actually holds together under load. When you look at the recursive to authoritative DNS, which constraint matters most? Processor choice, failure budget, or replacement cost? See you on the next incident review.